Okay, good morning, everyone, and welcome back from winter break. I know you're excited to be back. I always say that the day after, or teaching the day after winter break is perhaps the toughest day to teach or for learning. Okay, but here, today we're going to begin our study of exponential functions, and the COVID-19 crisis is a good illustration of what an exponential function is. Okay, so here I have a table or a graph of total coronavirus cases in the United States. And on February 28th, there was a reported 60 total cases in the United States. But by December 23rd, there were 21,113,528 total reported cases of coronavirus in the United States. As you can see, there was tremendous growth throughout the year. Good illustration of an exponential function. They grow very quickly, or they decay or decline very quickly. Let me ask this question here. So here's a question. Would you rather have $10 million today, or the value of a penny that doubles in value each day for 31 days? Okay, so the first day you'll have a penny, the next day it will now be, you'll have 2 pennies, and then the next day after that 4 pennies. Would you rather have the value of a penny that doubles in value each day for 31 days, or would you rather have $10 million today? Assuming you'll be alive in 31 days, what's more valuable? I'll answer that question at the end of the lesson. So let's take a look at exponential functions here. All right, so our objective today is to write and evaluate exponential expressions to model growth and decay situations. Some vocab: exponential functions, base. I always like to say the base 2, I say, is a multiplier. The multiplier. You'll see why I say that. Big key word here, asymptote. We'll talk about asymptotes a lot in this chapter and future chapters. And then we'll take a look at exponential growth and exponential decay. So here, the exponential function. The form of an exponential function that does not involve a percent, and we'll take a look at one that does involve a percent, is this: f of t is equal to a times b raised to the t. And it's always helpful to take a look at exponential functions with respect to time, because that's where they make the most sense. In fact, if I went back here and taking a look at the total growth in COVID-19 cases, we looked at that over time. Okay, so the general form f of t, so the function is a function of time, equals a. We say a is the initial amount. This is where things start when time is 0. And then b is a base of multiplier. Is how much it grows each day or each week or each year, okay, each t. So let's take a look here. So we have a table, and we see that at time 0, f of t is 10. Okay, so we have a table of values that give us time, and then we have a f of t. Now again, a is an initial amount. That's when t is equal to 0. That's where things start. So when t is equal to 0, f of t is 10, so a will equal 10. That's my initial amount. And then, well, what's b? One way we can get at b is just by taking the future date and divide it by the prior day. So here, so b here would equal, so if 20 divided by 10 is equal to 2, or I could say 40 divided by 20 is equal to 2. I'm just taking the day ahead and dividing it by the day behind for f of t. Or 80 divided by 40, that's equal to 2. Or 160 divided by 80, that's equal to 2. Okay. So b, my multiplier, is 2. In other words, every time time increases by 1, I'm doubling. Okay, so when I started when time was 0, I had 10. Okay, the next day I say 10 times 2 is 20. And then on the next day I go 20 times 2 is 40. And then the next day 40 times 2 is 80. and so on and so forth. So that's why we call it the multiplier. That's why b is called the multiplier, because we're just multiplying each day by the multiplier, each successive amount by the multiplier. Okay, so b is equal to 2. So my function here that models this table is f of t is equal to my initial amount, a, which is 10, times b, which is 2, raised to the t. Okay. Now, let's just verify. So when t is 0, I get 10 times 2 raised to 0, and anything raised to 0 is just 1. So this should just be 10 times 1 is equal to 10. And then when t is 1, I have 10 times 2 raised to the first, and 2 raised to the first is 2, and so this would just be equal to 20. And then when t is 2, I have 10 times 2 raised to the second, and 2 raised to the second is 4, and 4 times 10 is 40. Okay, so that gives us the value that we see in those tables for each t. So that function then represents that table. We modeled that exponential function given the values in the table. Now, if I were to graph that function on decimals, let me hide that one, you can see that that graph is growing really, really fast. When x is 0, 10 times 2 raised to 0, 2 raised to 0 is 1, and 10 times 1 is 10. And when x is 0, I get 10. Right there. That's my y-intercept. Okay, but as you can see, that graph grows really, really quickly. Okay, grows really quickly. Now, let me zoom in here. I want you to notice here that this red graph is getting closer and closer to the line y is equal to 0. But the red graph will never cross the line y is equal to 0, but it gets very, very close to it. You see? It gets very close. So this we would call an asymptote. And an asymptote is a place in the coordinate plane that a graph approaches, this red graph approaches, but doesn't cross. We say eventually that red graph just hugs the line y is equal to 0. Okay, it hugs it, but it doesn't cross it. So that would be considered the asymptote. Okay. Now let's go back out here. All right. So, and again, I graph that over here. So this would be considered the asymptote. My asymptote here would be the line y is equal to 0. Okay, it's an imaginary place in the coordinate plane that the graph approaches but never crosses. That exponential function is getting closer and closer to the line y is equal to 0. That's considered the asymptote. All right, now let's take a look at some more. So here I have another table. Okay, and I see at time 0, f of t is equal to 3. Okay, so my initial amount is a is equal to 3. Okay, everything starts at t is equal to 0. So a is equal to 3. Now b then, if I just take f of t for day 1 and divide it by f of t for time 0, so 9 divided by 3 is 3, or 27 divided by 9 is 3, or 81 divided by 27 is 3, so that would be my b. So my function that models this table is f of t is equal to my initial amount 3 times my multiplier 3 raised to the t. And then lastly, so, oops, here I have another table. Okay, at time 0, f of t is 1. Okay, so my initial amount is 1, so a is equal to 1. So b would be f of t at day 1 divided by f of t at time 0. So 4 divided by 1 is 4. Or 16 divided by 4 is equal to 4. Or 64 divided by 4 equals 4. So my function here would be f of t is equal to my initial amount, which is 1, times my multiplier, or b, which is 4 raised to the t, And we would just write that 4 raised to the t. Don't really need the 1. Now, all of those graphs, if I go back out to, so that was a graph f of t is equal to 3 times 3 raised to the t. As you can see, both of those graphs, they're growing really, really quickly. Now, let's take a look at this other table here. So here, when t is equal to 0, I get f of t is equal to 20. So a is equal to 20. Now let's find a multiplier, or b. So if I take 10 divided by 20, that gives me 1/2. Or if I take 5 and divide it by 10, that gives me 1/2. Or if I take 2.5 divided by 5, that gives me 1/2. So b, my multiplier, is 1/2, or 0.5. So the exponential function that models this table is f of t is equal to my initial amount, a, which is 20, times my multiplier, 1/2, or 0.5, raised to the t. Now, if I go out to Desmos, and if I graph that one there, so 20 times 1/2 raised to the x, you see that graph is decaying very quickly. Okay, in comparison to y is equal to 10 raised to 2x, that graph is growing very quickly. Okay, so we say this: when b is greater than 1, we have exponential growth. But when b is less than 1, a fraction, we have exponential decay. Y is equal to 10 times 2 raised to the x. b is 2 is greater than 1, we have growth. But here, when y is equal to 20 times 1/2 raised to the x, 1/2 is less than 1, we have decay. And b will always be greater than 0. It will never be negative, and it won't be 0. Okay. So, when we say that we have exponential growth when b is greater than 1. We'll have exponential decay when b is less than 1. But b will always be greater than 0. So b will always be greater than 0. So in this case here, when our base was 2, our multiplier was 2, we had growth. Here, when our base was 3, our multiplier was 3, we had growth. Here, when our base is 4, or a multiplier is 4, we had growth, because in each case our multiplier, or b, was greater than 1. But here, where I have b is equal to 1/2, I will have decay. Okay, the function will decay, as we see there, that green graph. b is 1/2. Right, and then the last one here, the last table here. So again, let's write a function, exponential function that models this table. Okay, so when t is equal to 0, f of t is 40. So my initial amount is a is equal to 40. And then 10 divided by 40 is 1/4. And then 2.5 divided by 10, that's 1/4, or 0.25. And so on and so forth. So here, that will equal my b. So my function will be f of t is equal to my initial amount, which is 40, times 1/4 raised to the t. And that, again, will represent exponential decay, because b, or my multiplier, is less than 1. Because if I go out and I graph this here, you see that represents exponential decay. 40 times 1/4 raised to the x. Right? So those were exponential functions that did not involve a percent. Now, let's look at those exponential functions that do involve a percent. The general form for an exponential function that involves a percent And it's a lot like what we just saw, except we just have to do one more thing to it. So f of t is equal to a times 1 plus or minus r raised to the t. Again, t is time, a is the initial amount, but here r in this case is the rate as a percent. Now remember how to change a rate to percent, you divide by 100. So if I have 5%, if I divide that by 100, I get 0.05. We have to convert r to a percent as a decimal. 1.2 we have to convert the percent to a decimal. 1.25%, 1.25 divided by 100 is 0.0125. We just move the decimal 2 places to the right, or left, I'm sorry. So 5%, 1, 2. Add a 0.05. 1.25, 1, 2. Add a 0.0125. Okay, we have to convert that percent to a decimal. Okay. So r is rate as a percent as a decimal, though. As a decimal. Convert that percent to a decimal. So here, let's look at some examples here. Tony purchased a rare 1959 Gibson lead guitar for $20,000 and $20,000 for $12,000. So the initial amount was $12,000. So we'll write f of t. The initial amount was $12,000, and then experts estimate that its value will increase by 14% per year. So 14% as a decimal will be 1.14. Use a graph to find the value of the guitar when the guitar will be 60,000. Okay, so we're going to use f of t is equal to a times 1 plus r. The rate is 14%, but as a decimal, so it'll be 1.14. 1 plus r as a percent, 1.14, and the initial amount is 12,000, so our function is going to be 1.14 raised to t. Now if we graph that, let's see here, graph that 12,000 times 1.14t. Okay, graph the function. We'll graph that using decimals and use the graph to predict when the value of the guitar will reach $60,000. So I'll go out to decimals. So 12,000 times 1.14 raised to t. So let me erase all of this. So 12,000 times 1.14 raised to the x. Oops, I got the wrong x there, didn't I? Why does that come up? Why do I not have, let me, there we go. Alright, so here, the graph, there we go. 12,000 times 1.14 raised to the x. And we want, oh boy, and we want to know when the value of the guitar is going to reach $60,000, or 60,000. It's going to be kind of tough to see here. Did I do this right? So y equals, okay. Why is everything, there we go, y equals 12,000 times 1.14 raised to the x. And when will it be 60? Oh, this is going to be really tough. Okay, well, we got to go wait until it's 60,000, huh? Yeah, it's not even. Well, it's kind of tough to estimate here. All right, so let's. So about 12.29. Let's see if we actually see that on decimals. It'd be better though. If That gives us about 11 or so. Kind of tough to get here. 60,000. Well, about 12 years, I guess. All right, about 12 years. 12.29 years using our graphing calculator. And then let's look at the last example here. The value of a truck bought for $28,000 decreases 9.5% each year. Write an exponential function, graph the function. Use a graph to predict when the value will fall to 5,000. So here, the initial amount is 28,000. So f of t is equal to 28,000. But depreciate means a decrease in value is decreasing 9.5% per year. So this is going to be 1 minus 0.095 raised to the t. So this would be 28,000 times 0.905 raised to the t. And we want to know when the value will fall to $5,000. Actually, this chapter will solve for t. Okay, but we'll do that towards the end of this chapter. Right now, we'll just graph using decimals. So 28,000 times 0.905 raised to t. So this is going to be 28,000 times 0.905 raised to the x. And we want to know when it's going to go to 5,000. Oh, there we go. Kind of tough. So about 17 years. 17.259. So let's see here. Yep, 17.3 years. All right. So anyway, those were exponential functions that involve percent. You just have to remember to change the percent to a decimal. Okay, if it's increasing, it's 1 plus. If it's decreasing, it's 1 minus.